So this is a recording about beginning to set up a phase diagram and fluid information and gather the information on a fluid in order to use it for computational thermodynamics and things like cycles and a variety of other applications. In this instance, we will be using, originally I told you in class that I would be using benzene. However, benzene does not have all of the data that I want. So I will be using ethane instead because it does have all of the data that I want. So for the sake of this, and none of you picked ethane, so for the sake of this, I'm going to use ethane. Not all of your gases are going to have all of these data. Your gases will have the bare minimum, and I will talk to you about how to get around and work with that, but they're not going to have all of these data. Some of them won't. In terms of the dominant thing that they won't have is the sublimation line and the melting line, but you can approximate the melting line, and I'll talk to you about how to do that. Okay, so let me share my screen now that I'm recording. I have Igor loaded underneath, and I've got Refprop up because Refprop is where we're going to start. Now, Refprop is something that you have to get access to through our department, so through me. And you would be given this file as part of thermodynamics, as part of the course. And you would also be, it's a requirement that you have to have a Windows-based machine for this. Now, first thing I'm going to do is make sure my units are okay. So my units should be Kelvin bar, liter, gram mole, kilojoules, molar based. So those are the units we're going to be working in for this course. So Kelvin for temperature, bar for pressure, liter for volume, grams for mass, moles for the amount of substance, and then molar based. The next thing you want to do is set which properties you want to see. And initially for what we're doing, temperature, pressure, and density. We don't actually need to see volume because we're going to be plotting temperature, pressure, and density. Later in the course, we will also be using a whole bunch of these other properties, but for now, temperature, pressure, and density. And property order, you should go ahead and move. Gibbs and Helmholtz tend to fall way down in this list. You should go ahead and move them up. And I would put entropy by internal energy. So I've made adjustments of the property order here. So my property order is temperature, then pressure, then density, then volume when we display volume, then internal energy, entropy, enthalpy, Helmholtz, Gibbs, then heat capacity at constant volume, heat capacity at constant pressure, because we use those. And then for me, you don't have to worry about this. I'm going to shift the dielectric up because later I will be trying to calculate that in some of my stuff. And I'm also going to shift the isothermal compressibility. Because again, that's something I will be using and calculating in some studies that I am doing. So while I'm here moving properties around, I'm just going to go ahead and fix that for me. and the adiabatic compressibility. And that's not anything you guys need to worry about. That's for something that I will be using later. Okay. But while I was there, I was going to fix that. So the very first thing I'm going to do is select my fluid. And the fluid I'm going to select is ethane for me. And then I'm going to look at the information. And I'm going to note what the triple point temperature is. And these are things that you should write in your notebook because you will be referring back to them. And then eventually I will get the triple point pressure and the triple point densities. Notice the plural there. And that's because I will have a gas, a liquid, and a solid triple point density. And then I have the critical point pressure. So 305, temperature. So you can see for ethane, the critical temperature is above room temperature. So that means ethane's a gas at room temperature. Critical pressure and the critical density. I will also write the units of applicability. So my temperature is good from 90.368 Kelvin, which is the triple point temperature. This is a fluid equation of state, to a maximum of 675 Kelvin. And just to see, I'm going to check and see what that maximum is in terms of what's called reduced temperature, which means I'm going to take 670 to 5 and divide it by the critical temperature of 305.32. That gives me a reduced temperature at maximum of 2.21. And I'm going to note that because when I do phase diagrams, originally I have isotherms defined in terms of steps and stuff in terms of temperature. So that tells me the farthest I can go temperature-wise for this equation of state. And I won't put any of the other extended temperatures in. I have a maximum pressure of 9,000 bar. And again, I'm going to take 9,000, divide that by the critical temperature, and that gives me a reduced pressure at the maximum of 185, which is huge. So I'm not going to be anywhere near the limits for that. But then again, I'm not ever, it would be hard to design a cell that handled such a high pressure. 22.419 moles per liter is the maximum density, and that gives me a reduced density of 22.419 divided by 6.8569 or 3.27. So that kind of gives me a range of my equation of state. Then I need to know what the errors are in the equation of state. What you're really looking for here is any really huge errors, any places where you really need to kind of worry about stuff. In terms for our work, the errors for the equation of state here are 0.02 to 0.04% in density, up to pressures of 300 bar. So we're probably fine. I would write these down in my notebook, but that's because I'm doing computational work. you guys do not need to worry about those. And then the final thing you need to check before you start doing anything is you just need to check and see what can you calculate. And the way you do that is you go to saturation tables. And in saturation tables, you'll see that for ethane, I've got a vapor liquid saturation. I have a solid liquid saturation, so the melting line, and I have a solid vapor. For some of your fluids, all three of these may not be active. You will always have the vapor liquid saturation, but you may not have the solid liquid or the solid vapor, and that is okay. So, and I'm going to now move off of that and go ahead and do a few other things about getting to know my fluid. So I'm going to go to Google and NIST Chemistry Webbook. And in the NIST Chemistry Webbook, I'm going to check to see if I have vibrations, and I do. So that means and it has the symmetry number. Life is very good. So I have a symmetry number of 6. For ethane, I should have, it's C2H6. So it's got 8 nuclei. So that means, and it's nonlinear. So that means I should have, in terms of vibrational modes, 3 times 8 is 24, minus 6 is 18. And then I will check this table. I have 6 A's, so 1, 2, 3, 4, 5, 6. And then the E's count twice, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yes, I have all vibrational modes. So I just need to write these down. So 2, 9, 5, 4. So these are vibrational modes, and they are in inverse centimeters, which means technically wave number. So 2, 9, 5, 4, 1, 3, 8, 8, 9, 9, 5, 2, 8, 9, 2, 8, 9, 6, 1, 3, 7, 9. And if you're just making a list of them, the way you note the doubly degenerate, like 2969, is I'll put in parentheses a 2 at the end because that, or a D2 to note that that's a degenerate orbital. 1468. Because that way I know I need to count that twice when I'm using it in calculations. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I was just double counting to make sure I'd written them all down. So that gave me the symmetry number and the vibrational modes. I'm not going to find the rotational modes here. I'm not going to find the dissociation energy here. So the NIST Computational Chemistry Comparison Benchmark Database is where I'm going to go to find the rotational modes. I'm going to look at experiment, one molecule, all properties. And I'm going to type in C2H6. Going to ask me what properties I want. I want the ground state. And then I have to wait. It's been really slow lately. So it's going to give me all the properties, enthalpies of formation, heat capacities at room temperature, same vibrational modes that were in the NIST database. And then the rotational constants, which is what I need. So I have A equals 2.51967 centimeters to the minus 1. B equals 0.68341 centimeters to the minus 1. C equals the same as B. Then it gives me geometric data. That would be if you were calculating bond descriptions. Sadly, the electronic energy it gives me is with the ground state at 0, which means that is not a dissociation energy. So that means now I need to go look up dissociation energy for ethane. So 620 kilocalories per mole. And you can kind of just use, how much energy does it take to break all the bonds apart? Because that is in essence what that dissociation energy is for a diatomic. So that is in general the way you do that. So the way to work that out is especially since a lot of you are working with a broad things. If you look up a bond energy table, then you can see that for a carbon-carbon bond, I have 348. This is in kilojoules per mole instead of calories, but it'll work. So I have 348. And for ethane, I've got a single carbon-carbon single bond. Plus I have 6 carbon-hydrogen bonds, so that would be 414 times 6. So 2832 kilojoules per mole. Now, let's see. If I convert, sorry, I didn't mean to sneeze, but 620 kilocalories per mole to kilojoules per mole, you'll see I get 2594. So it's very close. So if you are hunting the bond dissociation energy for your system and you just can't find it, you can calculate it using the bond enthalpy tables or the bond energy tables. But before you do that, I would inherently first just look up the dissociation energy and see if anybody has that, because there are some also So you can see as you break apart bonds and get it down, the energy changes, and that means the overall dissociation energy is different. So I was just checking to see if I could come up with a better way of getting the values. But in general, just look up dissociation energy because that is what you need for the dissociation energy part of the thermodynamic equation. Luckily, it's the thing that cancels out for all that it's the hardest thing to find. Anyway, okie dokie. Here. Fun. Okay. So that gives us all of the information that we need for ethane to get started. So in order to get my Igor set up, I will do that and the setting of the phase diagram boundaries in the start. Well, this video is not super long, so I'm going to go ahead and do that for this video of just getting my IgorPro set for what I'm going to do with it. So initially, this is what Igor looks like when you first load it. I'm going to set some data folders. I'm going to have a real gas data folder, a van der Waals gas data folder, and then a perfect gas data folder. And it'll be in the real gas data folder that I need to be in right now because I'm going to be setting phase boundaries. And, you know, in all honesty, since those boundaries we don't touch that much, I'm actually going to make a folder called phase bound, because that way I can put the phase boundaries in a separate folder. So that gets that started. Now, up here in Refprop, I'm going to shift that over there. So now I've got them side by side. I'm going to, I told you I needed to look up what the phase boundaries are. And what I need is the triple point. So the vapor liquid saturation phase boundary, if I set it to start at the triple point temperature and go to the critical temperature and step by, say, an increment, I mean, that's a fairly broad temperature range. So I'm going to step it by 5. So you can see it ended at 305.7. And now I'm going to generate a table in Igor by typing the word edit. That gives me a way of copying what I see here into Igor. And now I'm going to rename these to match. So this will be temperature. This is liquid gas boundary, pressure, vapor, because technically that's what that is. This is temperature vapor. This is the density saturated. This is the liquid density. So DL saturated. And this is the vapor density along that phase line. And then I can go ahead and display that. So I will display the vapor pressure versus the saturated liquid density. And I will append to graph the vapor pressure versus the saturated gas density. Now you can see in that graph, I have a huge gaping hole at the top because between my last point was 300. My critical temperature is 305. So what I'm going to do now is come back and now I'm going to calculate the saturated points at equilibrium instead of just a broad table. And I'm going to step it. So 301, 302, 303, 304. Now, I know for a fact that that thing gets flatter and flatter and it's going to become less and less smooth. So now I'm going to step finer because it doesn't take that much time to type. Until I get to the critical density. And you can see that even at 305.32, which is the critical point temperature as NIST gave it, I'm still not at equal density. So I'm going to actually put in the critical density, 6.8569, and let it calculate the temperature. So you can see how off it is. So I'm going to put in these and just copy and paste them. And you can see I've now got a smoother line, and then I'll put in the final one. And now I have my smooth phase boundary. So this is my liquid vapor phase boundary. I'm going to make this a heavy line because it is a phase boundary. So above that single phase, below that two phase. Now, my triple point densities for the gas is 1.52 01 times 10 to the minus 6 moles per liter. For the liquid, it is 21.668 mole per liter. What we don't know is the solid yet. So now I come back to calculate. Now I'm going to, again, calculate saturation tables, but now I'm going to do the solid liquid line. And again, I'm going to start it at 90.368. Now the solid liquid line can go to whatever final temperature I want it to go to because it keeps going up. So, but I'll probably at some point hit a solid, liquid, triple point, goes up in pressure. We'll see where it goes. And it tells me that I run out of density range. Yes to all, yes to all. So I quickly run out of the, and you'll also see it only gives me the density of the liquid, not the density of the solid. So in order to get the density of the solid for this, what I've done in the past to look up the triple point density of the solid is I've actually just looked it up. So our friend. So the density of ethane at solid ethane at triple point. Okay, so the density of solid ethane at the triple point is 206 kilograms per meter cubed. Now I have to convert that to moles per liter. So if I go to Refprop, substance, option, substance, fluid information, my molar mass is 30.069 grams per mole. So 206 kilograms divided, delete E to the third grams divided by 30.069 is 6850 moles. Wait, did I? Yes, I did divide. Good. Per meter cubed. Now, this is going to be the most convoluted thing. I don't think in meters cubed. But I do know that there are 10 to the 6 milliliters in a cubic meter. So I'm going to divide that by 1 e to the 6th. That gives me milliliters. And then I'm going to and then there's 1,000 milliliters in 1 liter. So if I now multiply that by 1,000, I get 6.85. Mole per liter, which is way less dense than I expected it to be. Means solid ethane definitely floats on the liquid. So I'm definitely going to recheck these calculations real quick. Yep, 6.85. Solid ethane did. That makes a lot more sense. 12.5 moles per liter. And it's triple point. Still less than oh, the reason is the molar mass. Oh, it's not. 12.5 moles per liter. Bingo. This is a really old paper. So you can see the triple point pressure is 1.130 pascals. And we have that. It is low. And the liquid density is 21.67, which we have. The vapor density is 1.504, which we have, and it does not have the triple point for the solid. And that's because for an equation of state, you don't need it. Two phase boundaries. If you're curious, this is the type of research paper that underlies the data in Refprop. And this is how they get all of the errors in everything that they quote in Refprop, and the biases and all of that information. And yeah, these are like 320-page papers. I don't ever print equation of state paper. Bingo. Now we're looking at data. So, well, that's ideal gas. Anyway, I think probably the 12.5 is accurate, give or take, although definitely got a 6 point something. I'm going to do one more search on this. Triple point density of solid ethane. Actually, 6.5 is what I got. 6.85 moles per liter. 0.65 grams per centimeter. So 0.65 divided by 30.069 is 0.021. That's grams per. And we want liters, so that times 1,000. That is 21. That's the liquid. Although it could also be the gas, the solid. So you can see the issue with this is finding the densities of the solid at the triple point can be problematic. And you can't inherently necessarily trust what the AI pulls up, that's really the triple point at the solid, because it doesn't always give you, I mean, it's not interpreting the data correctly either. So that means we don't really have the triple point, the density of solid ethane. But we at least have the density of the liquid. So what we'll do now is we will create this, because that is a phase boundary. So this is the temperature for the liquid, the melting line, so melt. This is the pressure for the melting line, and this is the density liquid for the melting line. And again, this is a phase boundary, so I'm going to make it hot, solid black. So now you can see, and for us, to be honest, I'm going to cut this off at, say, 1,000. That's a lot of pressure. And in fact, I'd say those last 2 points I'm going to get rid of. And that's just because a pressure vessel, here's why I'm going to get rid of that. A pressure vessel that we would feasibly work with in the lab is probably going to hold 200, 300 bar. Anything above that's going to get touchy. Even the pressure vessel I designed only holds 400 bar, and it's hugely well designed. So I'm going to cut us off at, I designed my pressure vessel for 400 bar, so 450 bar. So what I'm going to do is back this down, use the liquid pressure, and deal with this in a slightly different way. Still going to do a solid liquid saturation line. I'm going to adjust the temperature to 100 Kelvin. See, 90.368 to 100. And I'm going to step by 1. That gives me a more reasonable guideline and allows me to get up to 450 bar, which, as I said, is where my sample cell ends. And that gives me the pressure range that my equipment could deal with. And that's a good place to limit yourself, is if you know your equipment will only deal with a certain spot. And then the final thing we need to calculate is, again, saturation tables, but now solid vapor. Now, solid vapor is going to go from the triple point to colder temperatures. So that means I'll leave it at 50 because that's where it's automatically set up to go to 90.368 with an increment of 5 is again fine. And you can see, if you look at that, the pressure is tiny. The density is tiny. And if I look at that on this line, it is going to be almost unobservable. We will put it on here for completion. We're just not going to really be able to see anything. So this is temperature for sublimation, pressure for sublimation, and the density of the vapor for sublimation. And again, I'm going to append the pressure of sublimation versus the density of the vapor for sublimation. Need to change the name of that where it's consistent. I've just been using dV. And I will, again, lines between points, size 2, and black. Do it. You can't see it unless I take the time to, my mouse is grouchy. The only way I can see that is if I expand way up. And now if I change the color of this, actually, to hide all of those where we can see. That's that line. Notice it's 10 to the minus 6, 10 to the minus 6. The moment I redisplay any of these other traces, you can no longer see that little bitty dot because it's all the way over there in the 10 to the minus 6 region. So the sublimation line, when you're looking at the full phase diagram, you just really can't see it. It's tiny. Now, CO2, I might do CO2 for you guys to see because it's going to be where you can really see the phase boundaries again. But that's for ethane, that's the phase boundaries, and that's where we're going to stop for this video.